All right, now we are recording. So, hello. Last time we covered chemical shift and we covered signal types. For now, we are going to just move on, but you can ask me any questions about it afterwards, and I can also send you the YouTube link to this stuff that I cover. So, let me know, and I will be happy to share that with you. But moving on, the only thing we didn't talk about last time was the chemical shift equation. So, I'm going to go ahead and give that to you guys. The chemical shift equation is ppm equals hertz over megahertz times 10 to the sixth. And ppm is the, is the chemical shift. The hertz value, is the observed frequency. And the megahertz value is the frequency of the NMR spectrometer. And one thing that's super duper 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 important is this times 10 to the sixth is only here to convert hertz and megahertz. So for the purposes of this class, everything that he gives you will have the conversion in mind. Like, you don't need to do the 10 times, or you don't need to do the end 10. Oh my gosh, I just had a stroke. You don't have to do times 10 to the sixth at the end. So for our purposes, you're going to pretend that this equation is just ppm equals hertz over megahertz. Ta-da. And so he'll give you a big wordy question like this, right? But all you need to keep in mind is ppm, hertz, megahertz. In this example, they give us megahertz, they give us ppm. So if we set this up, we're going to say 1.25 equals x over 400. And then we would solve this by doing 1.25 times 400. At that point, it's just, algebra. And so our answer would be 500. And ta-da! Any questions? If not, awesome, we can move on. But if anyone has any questions or comments, don't be afraid to ask. All right, I'll take a sip of my water, give you a second to screenshot or write it down or whatever it may be, and then we can move on. I choked, I'm not dying. Okay, sweet, let's move on. We are not going to cover this for now. I will go over this in the exam review just for time's sake. So, all of this was a lot. Raise your hand if this was a lot. I think you can actually raise your hand, but you don't actually have to do that. I'm just trying to be funny. Anyways, I'm going to make a new page, and I'm kind of, oh, someone sent a smiley face. I love when you guys do that. It gives me so much serotonin. Okay, so I'm going to write separately from the handout because I want to have like a clean slate for you guys because it's a lot. And then once we finish with that, I will go back and let you know what goes where in the handout. If at any point you get confused, please just let me know. All right. So there's a couple different things that go into splitting. First of all, what's another name that we use synonymously for splitting? Start with M. Multiplicity, indeedio. Sweet. And tell me something, anything, whatever you remember about splitting and multiplicity. Anything at all that comes to your head. Complex and regular, n plus 1. Perfect. There's two other things we talked about. Let me see if you guys can remember. Okay, yeah, we're talking about J values, hybridization, number of unique neighbors. Cool. Okay, what's one unofficial rule that I gave you guys? It has to do with oxygens, nitrogens, sulfurs, fluorines. Yes, so the heteroatom rule, it cannot pass a heteroatom. Sweet. And how many bond lengths can you go through? 3. Sweet. So basic rules, n plus 1, where n equals number of unique I don't know why, but the word unique looks so wrong, and if I spelled it right, please don't spelled it wrong, please don't make fun of me. 3 bond lengths and hetero atom cannot split through. All right. Also, I really like the dots in the background, but it just occurred to me that it might bother some people. If anyone has a problem with that, just let me know. If nobody says anything, though, I will assume it's fine. Okay. So, yes. All right, so all of it correct. One thing you guys have to talk about that we didn't really mention yet is J values. What's another word for J value?
Integration.
Starts with the C.
Oh, yeah.
Coupling constant. Yes. Okay. So, oopsie. Oopsie. All right. So, we're going to talk a little bit more about coupling constant and J values. So, for the purposes of this class, you don't really need to know too much. Curve. Oopsie. Could you chill for like 1 second? Related to the R plus curve. I'm not gonna. Oh, can you guys hear me again? People were saying that I was like breaking up. Yes. Okay. Sweet.
Yeah, you were breaking up.
I don't know why. Like whatever. Basically, it's related to the car plus curve. I'm not going to cover the car plus curve because he's not going to ask you a question really about the curve. Um, all you really need to know is that it exists and take a quick look at it on your own and just get an idea of what it looks like. What you guys need to also know is that the J value is, so sorry, J value is essentially the Hertz value by which one signal splits another. I know he covered a lot more, and there's a lot more to this, but genuinely, you don't need to know any more than this for the purposes of the exam. And something someone mentioned is hybridization. So you need to know that different hybridizations have different J values. And what else has different J values? That's a very vague question. But what's something he talked about with J values? Double bonds, triple bonds, but also something that looks like our friend benzene. Phenols, kind of, we're going to say, kind of, rings. Yes. So we're going to say different positions on cyclohexane rings have different J values. So what I mean by that is, let's say we have a chair, and if you're anything like me, you hate the chairs. They're so ugly. Whatever. Um, but we're gonna have a hydrogen pointing up here, down here, down here, up here. So what is it called when they are slanted like this? Equatorial. So what's it called when they're straight up or down? Axial. Cool. So I'm going to highlight the axial in yellow, and I'm going to highlight the equatorial in blue. So these different hydrogens are going to have different J values between them. So for example, this axial one is going to split this equatorial one at a different value than it's going to split the other axial. So does anyone remember any of those values? Oh, it's telling you that apparently my speaker is off. So that's awesome. If you said anything and I ignored you, I did not mean to, I promise. I think I should be able to hear you now if anyone else saying anything. I'm gonna do an awkward dance.
Hello?
Yes, hello. I can hear you.
Oh, I thought you were trying to do like a testing mic thing.
No, no, no.
Okay.
I can hear you guys now. Someone unmuted.
Okay.
Hey, dummy. Your volume is off. You can't hear them. Um, so I was just letting you guys know if anyone said anything and I ignored you, my bad. I didn't mean to. Okay, so someone said, what's the question? All right, so my question is, Dr. West went over a whole bunch of J values, and there's a whole bunch in your PowerPoint. Do you remember any of them at all? Okay, sweet. So we're starting somewhere. All right. So here, let me draw out two more things. Okay. So someone said geminal is 12 hertz. What does geminal mean? What what's the relationship between those hydrogens? same carbon. Super duper duper. Okay, so this hydrogen and this hydrogen have a J value of between 12 and 15 hertz. Sweet. And then someone said 7 hertz is for those that have free rotation. You're on the right track, but for the purposes of this, we're going to keep it even more simple than that. And we're going to say vicinal hydrogens are going to have a value of 7. And so what does vicinal mean? What does vicinal mean? Adjacent. Awesome. So, yes, also neighbor. So the two yellow hydrogens, I'm not implying that they're the same two words. So when they're on the carbons next to each other, they're vicinal, and they are going to be 7 hertz. That's kind of like our normal standard splitting value. Okay, so now within the ring, you need to know axial, axial, equatorial, equatorial, and then equatorial. It's okay if you don't remember any of these ones, but does anyone want to give it a shot? Because I know he mentioned at least one of them in class. Haha, I knew it. So axial, axial, yes, it's 14 hertz. I'm going to do it in yellow just to keep constancy. And that is going to be this and this one. So the J value between those is 14 hertz. And the other ones I'll just give to you. Equatorial, equatorial is between 2 to 5 hertz. And equatorial axial or axial equatorial is 4 to 6 hertz. So pretty similar. Wink, wink, nudge, nudge. If Dr. West were to ask you a question about this, it would probably look something along the lines of, what is the J value for these two protons? And theoretically, if he asked you that question, what would you guys answer with? 14 hertz. Awesome. Wink, wink. Nudge, nudge. The other one he likes to sometimes give just to be spicy is this guy. And as you can see, this is not regular coupling. It looks weird. And we call this W coupling because it sort of looks like a W. And the value for W coupling is going to be between 0 and 2 hertz. So I will keep that up there for you as well. So this is pretty much all you need to know as far as J values and coupling constants. Is this sort of kind of all right so far? Someone said check, and in my mind, it was like a check mark, and I don't know why that was so funny to me. Cool. I spilled water in my mask. And that was recorded. All right. So, and someone asked if I can review coupling one more time. So, of course I can. I am just going to explain it in a slightly different way real quick. And then if you want me to, I can go back and repeat all this, like what I said here before, if that doesn't make any sense to you either. So he went over tree diagrams, and that was another thing where I could feel everyone being like, what in the absolute world is freaking going on here? So, I will let you know, you do not have to ever make a tree diagram. You will never have to reproduce it. Sweet. Perfect. I will show you what a tree diagram is and how it works solely for the purpose of understanding this stuff conceptually. Because to me, it is important that you understand it and not just memorize it. Um, and this tends to help a lot of people with understanding. If I say it and you're still like, I have no idea what this means, pretend it doesn't exist. That's okay. All right? Okay. So I'm going to zoom in. And again, I'll zoom out so you can see. I'm so sorry. I just realized how the thumbs up works, and it was a magical moment. I'm so sorry. Anyways, um, yes, coupling. So I'm going to give you two molecules, and we're going to do normal and complex splitting. So normal is between same J values. And so, for example, let's say I have a molecule like this. And I'm going to draw out my red hydrogens here. And I'm going to draw my blue hydrogens here. And I'm just doing wedges and dashes because I can. That doesn't necessarily mean anything. A, B, C. All right, so first, let's do this the simple way. We're going to use n plus 1. And for the purposes of this example, we're going to focus on the red hydrogens. So how many neighbors does a red hydrogen have? 3. Perfect. And it has 3 because 1, 2, 3 bond lengths. 1, 2, 3. There's nothing on the other side. So we have 3 blue neighbors. And so in total we have 4. And what is it called when we have a multiplicity of 4? A quartet. Spectacular. So what in the heck does this mean, right? So I'm going to get the big marker out. So we are going to start with a red signal, right? And we are going to start out with just one signal. So this line right here represents the signal that is these two hydrogens. Eventually, this signal is going to be split by each of these blue hydrogens. So in total, it will be split 3 times. So first, HA is going to split it like so. And what is our J value for vicinal hydrogens again? 7. Yes, so this is 7 hertz. And so, okay. At first, we have 1 peak because it hasn't been split. Once it's split 1 time, it's like that. It has 2 peaks now. So after HA, it's also going to be split by HB. So now each of these two is getting split. So bam, bam, bam. Now, what's different in this level that wasn't here is now this line has overlap, right? So we have two separate lines overlapping each other. So I'm going to make this a thick, chunky line. So we know there's overlap. And so when there's overlap, that thick, chunky line is going to correlate to a taller peak. So we have a small, a tall, and a small. We are not done yet because we have a third hydrogen. So the third blue hydrogen is going to split this one more time. Before I write that down, I just want to take note. What is the hybridization of this carbon right here? I'm going to zoom in. The red hydrogens, what is the hybridization here? So, you know how we have sp, sp2, sp. Oh, yes, what was that?
I said sp3, but I don't know.
Yes, yes, you do know. You got it right. It is sp3. And so what's the hybridization of this carbon?
Same thing.
Same thing. Awesome. Okay. So in this case, we don't have a ring and we have the same hybridization. So that's how we know it has the same J values. Before anyone says it, yes, in real life, in real chemistry, this is more complicated, but we're not in real life. We're not in real chemistry. We're in Orgo 2. So this is good enough for this class. Okay? All right. So again, I'll reiterate, since we do not have a ring, and since they are the same hybridization, we know we have the same J values, and so it's normal splitting. So that being said, the reason I even point that out is because this is also splitting by a value of 7. That's why we have the overlap in the middle. And so our last hydrogen, excuse me, could you work? That would be so sick. Thank you. All right. So our next hydrogen is going to do the exact same thing. Bam, 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 bam. All right. And so before I draw the lines, I'm going to have you guys tell me whether it'll be normal or, excuse me, or thick. And you can just say N or T, right? So this first line, will it be normal or thick?
Oh,
Normal, yes. Okay. So what about the second one? Thick, yes. Well, okay. So I'm glad you, hold on, I'm sorry, I can't write and think at the same time. So a lot of people said normal, but some people, oh my God. Most people said thick, but a couple people said normal. So the reason it's going to be thick is because it's where two lines meet. And so we have overlap right here. That's why it's going to be thick. So with that idea in mind, what about this line? Will it be normal or thick? Ooh, we got some mix again. So let's see. It would have this side would make one. This side would make another. So since we have that stacking on top of each other, this one is also going to be thick. And again, whenever you have two sides splitting and it meets in the middle, that's when we have a thick overlap. And so what about this last one? Normal, sweet. All right. And again, all these values, 7, 7, 7. So now, when we draw our little peaks, right, we're going to have one small, one big, and one small. Because again, we have a tiny thin one, a big thick one, a tiny thin one. So far, did that sort of kind of make sense? If I completely lost you, please let me know. Some people said yes, some people said sure, and I read that in like a sure voice. That's okay. As long as you don't feel like you're in Nebraska, like you have no idea where we are, it's good. LOL, I get it. I'm just picking on you. Okay. So, yes, okay, good. We're not as confused as we were when we got here, I hope. So this is normal splitting. That's a normal tree diagram. That's it. And all it's really telling you, like, you got all this information here that you get from the tree diagram, but what you get from the tree diagram that you don't get here is that you're understanding what splitting means. So splitting is when each of these hydrogens break the signal into two separate signals, or two separate peaks, excuse me. So the one signal goes to two peaks, goes to three, goes to four. Any questions before we move on to complex splitting? While I give you guys time to type, I am going to send you the attendance link. Pretty please do that if you have not. Any hoops. All right. So the same J value has the same hybridization and same. Okay, so let me think about how to word it. So basically, when we think about J values for the purposes of this class, you're going to look at something, and we mentioned here that different hybridizations and different positions in a cyclohexane ring have different J values. So when you look at a molecule on the exam, you think, is there a ring? In this example, no, there isn't. And then you look at the hybridization. Are these the same hybridization? Yes. So therefore, they're the same. If one of them was sp2 and one of them was sp3, then they would be different. And if they're shown to you in a chair where they have different like positions like this, then they're different. But he's not going to give you a chair like this and tell you to do the splitting because that's mean. And then could we do an example question? So yes, but also the way he asks these questions are mostly just like, what is the splitting, or what is the multiplicity of this? And so like if he gave you this example, you would just say quartet. I do have some examples, I believe, but yeah, we do. Okay. I just want to do complex splitting and then we can do examples. Because complex splitting is annoying. All right, so let me make another page because your girl writes largely. Alrighty. So complex splitting is when we have different J values. Gasp. All right. So, guys, what are we going to look out for to see if we have different J values? This is new material. We've never talked about it before. Hybridization, yes. Okay, and the other one is two different neighbors, yes, but something else. If I just slip and come up here. Different hybridization and different orientations on the ring. Yes, positions on the ring. Exactly. Thank you so much. All right, so different J values. We know rings and hybridization. That's the things we're going to focus on. So I am going to give you this. And let's do some green, because why not? All right, hydrogen, hydrogen, hydrogen. So, my lovelies, if we're looking at the red hydrogen, how many neighbors does it have? 4. Cool. So are we going to use the n+1 rule for this example and be done with? No, because this is complex splitting. Does anyone remember what I super briefly mentioned once? Yes, you guys are killing it. Okay, so for complex splitting, instead of n+1, we're going to use n+1 times n+1. And this is something I kind of made up, so whatever. And I say NA and NB just for the two different neighbors so people don't get super confused. Again, this is an official formula, so don't be like, Dr. S, this is the formula whatever, you know. So anywho, if we're using the red hydrogen again as our kind of starting place, on the left side, we have how many blue neighbors? 3. And then we have 1 green neighbor on the other side. So we end up with 4 times 2. And I know you guys can do simple math, but there's a reason I wrote it out like this. Trust me. And the answer is going to be 8. And so an 8 is called what? An octet. Okay, cool. Someone called it. So in this case, since we didn't do normal splitting, we can't call it an octet. We're going to call it instead a quartet of doublets, or a doublet of quartets. And I'm going to show you why that is. Okay, so you can't just say multiplet in this example. I know I said anything after 5 is a multiplet, but when you have complex splitting, you have to be more specific. Yeah, that's it. Yeah, it just requires you to be more specific. I am sorry if I confuse anyone, but I'm going to change this just a tiny bit because we're running out of time and I don't want to make this example too complicated. So we're going to say 2 neighbors plus 1. So it's going to be 3 times 2. So our new answer would be 6. So does anyone want to take a guess at what the name would be in this case? A triplet of doublets, exactly, or a doublet of triplets? All right, so I apologize if anyone got confused. I basically just changed it from 3 hydrogens to 2. So, what is the hybridization of this carbon?
Three.
sp3, perfect. What about this one?
2.
Yes, sp2, cool. And this one?
2.
Yes, also sp2, sweet. So now we have different J values. So the J value between this and this will be much different than this and this. And so I am going to give you guys, just to make this math easier, I'm going to give you an arbitrary J value. This is not necessarily the right J value. You guys don't need to know what these actual J values would be, But for simplicity purposes, I'm going to say this is 10 and this is 5. Yikes. Could you chill? Anyway, whatever. So when we are drawing it out, we are going to start with the red hydrogen again. And it's just going to be a line. And it's a singlet so far because it's just one single peak. And to make it look nicer, we are going to start with the bigger J value so that the tree doesn't look super ugly. And I'm sorry I keep moving it around. I just don't want to run out of space. So in this case, the bigger J value is blue. So we're going to split it how many times by the blue?
2.
2, exactly. So let's say, bam. I don't think that that's even. Ta-da. All right. So this is by a value of 10. And the next time we split it is also going to be by a value of 10. So, yikes. Could you chill? We get the same response as before, or the same, I guess, answer as before, where the one in the middle has overlap. So it's going to be thick. Any questions so far?
How come we didn't split the other example we did in 2, though?
So this one? So what do you mean, like, about the splitting thing?
Like on the just now we did it. We did the 10 twice. Well, 3 times
So
I
we
would
split
say.
it in 2, and then again we split it in 2. This is just by a value of 7, and then this one is a value of 10. So we're not done yet, but I don't think I understand your question.
And then I'll see if I get it.
I have a question, Rosemary.
It's okay. We can come back to it, I guess. All right.
I was gonna
So
ask a question
we
real
are going
quick.
to split it one more time, and we are going to split it by a value of 5. So
Someone's trying to
each of
ask.
these 3 will be split into
Excuse me.
2 with a green. Yeah, I know someone had a question. They just either I can't hear you for some reason anymore, or they didn't like ask again. So if you still have a question, they're talking. I don't know why I can't hear you. All right. Let me try something super quickly. Okay. Try again. I should be able to hear you now.
I was gonna ask for the. Can you hear me?
If you are
Can
talking,
you
I
hear
still
me?
can't hear you. This is so sad. Uh-oh. Yeah, I don't know why I can't hear you anymore. Yeah, please try writing it if you can. My WebEx is being a dodo bird today. Okay, the doublet of triplet splitting we did That was for the red hydrogen. Yes. So we are looking at the red hydrogen. We're starting with the red signal. So absolutely correct. And in the other example as well, we're doing the red signal. Yes, so that's its multiplicity. You're right. Mm-hmm. Okay. So let me just. Okay, someone asked a question about the J values. I will cover that in 1 second. I just want to finish the tree so it doesn't confuse anyone too much. Um, so we're going to split this by a value of 5. And we can see here that there's no longer overlap, right? It looks a lot different than the third step here because it's no longer uniform, right? So let's go in and fill in the little peaks. So at this point, we would have 2 normal peaks, and this peak will have 1 tall one and 2 short ones. And then this last one will actually have 2 short ones, and then further away, 2 short ones, and then further away, 2 short ones. So we have basically 3 sets of doublets. So we are going to have a triplet of doublets. And I wrote doublet of triplets, and on the exam, those two are interchangeable, but I am going to change it to the more correct name. So again, both names are interchangeable for the purposes of this exam, but the most correct one starts with the bigger one first, and the second one being the smaller one. And yeah, I'm so sorry to anyone who just joined because it said 12:30 on Canvas. I didn't realize until like halfway through the session that I had made a mistake. So I am so sorry, but it is recording, so the recording will be up, and there is an extra session at 1:30. So I do very much apologize for my mistake if you got confused. Basically, SI will always be at the same times every week. So yeah. I think this is a good place to finish off for right now. Um, I will be back at 1:30. So, yes, a lunch break. Or if you're like me, a boba and applesauce break. If you think that's weird, then I was just joking. Okay, so let me answer that one last question. So, for complex splitting, the reason we know it's complex is because we have different J values, and we know that they have different J values because they have different hybridizations. So the red has one that's sp3 and one that's sp2. So they are different. We could also tell they were different if they were in a ring and they had different orientations in the ring. But he's not usually going to give you a ring because that's more complicated. All right, so let me go back to where we started today, and I will make it so you guys can take pictures. Let me know, or I'll give it like 30 seconds and then I'll go to the next one, and then we can work from there. Are you going to upload this on YouTube right after? Yes. So hopefully it won't take too long, and I can upload it before the 1:30 session. That's my goal. So the link will be in WebEx. Like it should be on Canvas to you guys right now. I was gonna send the Zoom link, but I'm not 100% sure if I'm gonna do that yet. So you're very welcome. Goodbye. And at the 1:30 session, we are going to finish up the last little bit of NMR. and mass spec, and then we are going to do chapter 11, I hope. You're very, very welcome. Have a wonderful day. For some reason, I can't hear you guys, but if you, I will be staying like an extra minute or two to answer any questions you guys might have. Oh, let me go on to normal splitting. So yeah, if anyone is confused, I do really apologize. The sessions always start at 11:30, but I accidentally input 12:30. Um, so that was my mistake. I really do apologize. The session ends at 12:30, but I am doing an extra session today at 1:30, and this one was recorded, so it will be up on YouTube in like an hour, the latest. You're so welcome. All right, and then the last thing we did today was complex splitting. Is the 131 the 131 is on WebEx. I said Zoom, didn't I, in the email? I probably said Zoom. I meant WebEx. I apologize. I'm just used to my classes being on Zoom. Um, but I will send a correction. It's 1:30 on WebEx. And oh, I said Zoom for the exam review. I will fix that. All right. Thank you so much for letting me know. Bye. You're welcome. See you guys later. Have a wonderful day. I'm going to close this.